Swayam Prabha. Digital India. Educated India.
So, what we will do now is to finish off the Measures theorem, right, which we started out yesterday, and then I'll also, like I usually do, I'll point out programming exercises as we go along, and then we will study shortest path algorithms. Right? So that's the plan for the about 1 hour 15 minutes from now on. So let's just quickly recall. The Measures theorem is about this parameter associated with graphs called connectivity, and like I pointed out, when I talk about graphs, in this case, depending on the context, if you pay attention, you can understand whether it is for directed graphs or undirected graphs. All the statements that are made, right, work for undirected graphs and directed graphs. Right? So we define a parameter called the vertex connectivity of a graph. To define the vertex connectivity of a graph, we consider a pair of vertices, right, S and T, and ask what is the minimum number of vertices that you must remove such that there are no S to T paths in the graph. Okay. Now, this number is called the ST vertex connectivity. Right? It's called ST vertex connectivity, as you can see here. Right? Now, the Measures theorem says that for every pair S and T, the maximum number of internally vertex disjoint paths from S to T is same as the ST vertex connectivity. Right? So in the example here, you can see that the vertex connectivity, right, of this graph is basically 1. You can remove one vertex to disconnect this part of the city, right, from this part of the city. Right? Because you will, and you can see that the number of vertex disjoint paths that you can have is only 1, because every path from this part to this part, right, will have to go through this edge. Right? So therefore, it's kind of intuitively clear that if you have to remove k vertices to disconnect S and T, then you will have k internally vertex disjoint paths. The focus on internally vertex disjoint is to observe that S and T will be common, no other vertices on the paths will be common. That's what we mean by internally vertex disjoint. So these are the pictorial statements. We actually prove a slightly stronger statement which says that if A and B are subsets, and if the vertex connectivity of A and B is given by this number k, this variable k, then there are k internally vertex disjoint paths from A to B, where A and B are two sets. Right? So recall that the first vertex on this path is from A and the last vertex in this path is in B. Right? Every other vertex is outside both A and B. Fine. That's what we mean by a path in this context, path from A to B. Fine. So now we will prove this by induction. Right, and we looked at a couple of base cases. Let me quickly run you through the base cases. Right, if B was the whole vertex set and A is a subset, this is really the base case. Right, it means that you have to remove all of A to ensure that there are no paths from A to G. If you don't remove a vertex, then there will always be a path from a vertex in A to itself inside the graph G, and therefore you must remove all of A. Right, so therefore the Measures theorem is clear in this base case, right. So therefore we will prove the theorem by induction on V minus B. So when B is equal to V, the boundary value is equal to 0. Right. So let us look at the statement that we will prove by induction, that's in the next slide. It's a statement which can be converted into an algorithm, right. And if you wanted to find the vertex connectivity for a pair S comma T, it is this theorem that you will convert into an algorithm. Right. So let us look at the statement. It says that if you have A and B, right, and the connectivity is K, and if you have n internally vertex disjoint paths that are from A to B, where n is less than K. So the connectivity is this number on the right hand side, and you have lesser number of vertex disjoint paths or internally vertex disjoint paths. Then we are going to prove a theorem that you can improve the number of vertex disjoint paths, right? That is, you can get one more vertex disjoint path, right? Where each path Qi is from, Q1 is from A to B, Q2 is from A to B, and so on. The endpoints of P1 to Pn are present as the endpoints of Q1 to Qn plus 1, right? So whatever was, so it may have been rewired like this. I think of this as rewiring the paths, right? So A1, B1 is like this, the path might have become A1 to B5 and so on and so forth, fine. It is also quite possible that you may add an additional path from A1 to B1 itself. That's also possible. Not necessarily An plus 1 and Bn plus 1 are new vertices, fine. So essentially you will discover one more internally vertex disjoint path. This is what we are going to prove by induction on V minus B. That's what we are going to do. Fine. So now let us set up the induction. This is where we stopped yesterday. Okay. Fine. So first thing, what do? You already have. So just let me emphasize again. What you have is this part A and B, these two sets, and you have n internally vertex disjoint paths from A to B, and we want to get one more internally vertex disjoint path from A to B. Fine. All right. So to do this, what do? You take a path from A to B, right? So whatever be this path, you call this path R, that's what we call this, right? You calculate such a path. If it turns out that R is internally disjoint from all the paths in P, your work is done. You simply consider the set P union R, fine, right? So therefore the theorem is being proved now. If R is not internally disjoint, this is the second case, then we have to do some interesting things. So to do interesting things, we will somehow use our induction hypothesis. We will set up the induction now, right? So what do? We look at this path, right? So let me look at this path again. Let me just draw on top of it again. So this is the path. You keep asking, is this vertex intersecting any of the existing paths, right? You pick the last such vertex. This is well defined because R is not internally vertex disjoint, right? So there is one vertex which is common to some path. Pick the last such vertex. That vertex is X, right? After that, all the vertices on R are not in any of the paths that you have inside P, fine. So this is the situation. So now we are going to use the induction hypothesis in a clever way. So what do? We are going to now define a new set B prime, right? B prime is going to strictly contain B, which means it will have at least one more vertex than B. What are the vertices of B prime? It has B, it has all the vertices on the path R after X including X, right, which is all the vertices here. It ends in B, remember, it includes that last vertex also, fine. It also contains all the vertices, right, on the special path P, right, which occur after X. What is a special path? It is that special path is the one on which X occurs inside the set P. So remember that P is all these internally vertex disjoint paths, X is occurring on one of them, that path is called P. X won't occur in two of them, right, because those paths are all internally vertex disjoint. So X will occur in one, that path is called P. So we take all these guys, including the last vertex obviously, right. So XP means all the vertices from X on the path P up to the end. So think of P as this ordered path. Okay. This is our B prime. Now observe that B prime is definitely one vertex larger than B, at least one vertex larger than B. X is the additional vertex, because X was on one of the paths, it was neither in A nor in B. So B prime is a strict superset of B. Therefore, V minus B prime is a smaller set and we will apply induction on A comma B prime. Fine, right? And with one additional path. How do we do this? Okay, so now let's move. So this is that was a review, right? Now apply induction hypothesis on that script P minus, remove that path P and union, right, X P X. So let's just go back to that picture now, right? So instead of P, instead of the script P, I am going to create a different set of paths with the same number of paths. What is a different set of paths? I remove this whole path P, right, and I put this path, this section, this part is called XP, sorry, this part is called PX. Those vertices on the path P up to the vertex X, including the vertex X. Fine. Observe that I have set up the induction carefully. All the paths end in B except this newly added path which ends at X, which is in B prime. Right? Fine. Consider this set of paths. How many paths are there? N of them. Recall that there are n paths. Right? And consider the partition A comma B prime. Fine. Right? So this is actually strictly larger than B, so V minus B prime is smaller. Right? Now let us carefully apply the induction hypothesis. Right? To apply the induction hypothesis, let us make one observation. What is the connectivity of G comma A comma B prime in relation to the connectivity of G comma A comma B? I want you to fill in the inequality here. Which connectivity is smaller? If you have to disconnect A and B, if you have to remove a certain number of vertices, if you want to disconnect A and B prime, if you want to remove a certain number of vertices, where should you remove more number of vertices? Okay, so let me help you with a picture. There is A here, right? There is B here. With respect to B, where is B prime? What is the relationship between B and B prime? B prime is a superset, right? Right. So now if you, which of the two sets, so now what is the relation? Does this picture help you? So if you had to disconnect A and B, if you had to remove, let us say, this box set of vertices, right, would you have completely disconnected B prime also? So you may have to remove one more vertex, no? Because B is a strict subset, right, of B prime. Therefore, the inequality is in this direction. Right? Why is this important? This is important because the number n is lesser than or equal to, is strictly lesser than GAB. You know this. Why do you know this? You know this from the premise of the theorem. When you started out, you said connectivity is AB, we have n paths, n is strictly smaller than the connectivity, right? And this you know is now lesser than or equal to K, G, A, B prime. Now you are ready to apply the induction hypothesis, right? Induction on V minus B prime. So what do you have? By applying the induction hypothesis, right, we know that there are Q1 prime, Q2 prime up to Q n plus 1 prime, right, connecting A comma B prime. So it's a connector. You have n plus 1 vertex disjoint paths. I hope you appreciate the usage. This is a conclusion that comes from the induction because V minus B prime is strictly smaller than V minus B, right? And you have one more additional path. Fine. From this additional path, we are going to get our Q1 to Qn plus 1, right? Now the aim is modify Q1 prime to Qn plus 1 prime to get Q1 to Qn, which is n plus 1 disjoint paths for A comma B. This is the last few steps of the tricky proof. Right? Now let us just observe how to do this. To do this, let us make some small observations. I'm sorry, so you can anyway take notes from this later, right? So the first observation is that X is the some path which is Q1. Let me call this Q1 prime without loss of generality. Let me just name that particular path, right? The induction hypothesis guaranteed me these internally vertex disjoint paths. One of them will definitely end at X, right? Let's call that Q1 prime. 2. N of them will end at, can somebody complete this for me? N of them will end at B. Sorry. N minus of 1 of them will end at B. Right? Very important thing. See, this one was ending at B. I removed it and replaced it by this fellow which is ending at X. Right? So Q1 prime is ending at X by the induction hypothesis. How many other paths are there which are ending at B in this particular set now? N minus 1 of them. So N minus 1 of them will end at B. How much have we accounted for? N minus 1 plus 1, N only. Then, right, one additional path. At a vertex Y, right? Where is this Y? Can somebody tell me? So let us, just to help you answer the question, correct, B prime minus B, that's a good answer. But in particular, for you to complete the proof, it is important to understand that Y is going to be in this union this, right? So let me elaborate this picture on the next, the slide that I am working on at the moment, right? So recall what we did. We had A. This was the situation with P. Okay, these paths were there. The last guy had X here, and some path started off like this, did some things, came here last, and then came into B and stopped. Right? This path was called the special path P. Right? This section is called P up to X. This section is called everything after X on P. This section is called everything after X on R. R is the path our algorithm found. P is the path which was there at the beginning of the iteration, that you have lesser number of paths than the connectivity. So where does this Y occur? Y occurs, as you correctly pointed out, Y occurs somewhere here. Right? Because those are the new vertices that you have added into B prime. Right? Those are exactly the new vertices that you added. Y occurs there. Fine. Now let us see how to fix it. There are two cases. Right? And the proof is almost done. Let us consider the first case where Y is here. Right? What will you do? you will take this path, you will take this path, you will take this path, everything you will take as it is, right? N minus 1 I will take, I need to add 2. How will I add 2? Remember that one of these, this one additional path, let me call this q prime n plus 1. Fine. This q prime n plus 1, where does it end? It ends at y. It starts some vertex here and it ends at y. Remember, it is internally disjoint with everything else, all the other paths that you have constructed. Right? That's the way we constructed it. So what do? You take this path and you go here and stop. That's one path. N minus 1 plus 1. Then you take this path p to x and then go on Rx, xr. Right? So the two paths that you take, qn plus 1 prime, which ends at y, followed by everything on p up to y. This is one additional path. The second additional path that you put in is everything that brings you up to p, right, and then go from r to x. Everything on the path, okay, making the same mistake again, I am sorry, p up to x, from x on r, this whole path. Fine. So consider p1 to pn minus 1, comma, this path and this path, they are all internally vertex disjoint. Fine. As you can see, the picture has convinced you that it is, I mean, it just requires small bit of writing to argue that this path, which is this guy, right, is internally vertex disjoint from this path ending here. This is one case. Fine. So what is the second case? The second, can somebody tell me what is the second case? So what is, where was y in? So case 1. What is case 2? Y could have actually been in xr. It could have been here. Right? Y could have been in xr. A similar patching argument will work. So let us look at the picture. Comes to x, right? So this is px, right? xp, right? And then you have your qn plus 1 prime, which comes up to y, right, and stops here, but y is on ry. So what do you patch now? qn plus 1 prime up to y, concatenated with, okay, again I make this mistake, I am sorry, yr, that is a path, and keep the old path itself, right? px concatenated with xp, right? So that basically gives you a additional path. Fine. Right? So it's quite an intricate proof. The proof is done, right? Fine. So like I pointed out at the beginning of the proof, it's present in page number 50 of Diestel's graph theory textbook. I've just essentially stuck to the exact same proof. You can also read it and it will become much clearer, but reading is not the only thing, right? Write a program, right? So take a graph, take a pair of vertices S and T, take n vertex disjoint paths, start with n is equal to 1, right, and increase it to 2, right? That's a good starting point. Fine. So this completes the vertex connectivity case of the Menger's theorem, right? So let us summarize this. Right. The vertex connectivity GAB is equal to the number of by the way, there are a couple of statements that I should say. Till when can you keep adding this additional path? exactly, till it becomes equal to the vertex connectivity. Fine. At that point of time, you can just stop. Fine. And therefore, this single step which we have just proved by induction, right, helps you show that you can keep increasing the number of internally vertex disjoint paths if the number of paths is less than or equal to the connectivity. Fine. So that completes the whole measures theorem proof, and this is what we have just proved. Right. A simple modification of this theorem, right, which I will not prove, is that the edge connectivity, as you can guess, is the number of pictorially, if this is your A and if this is your B, to disconnect A from B, if you have to remove these 3 edges, then there must be 3 edge disjoint paths from the set A to the set B, and that is exactly 3, right, must be 3. Right? So one direction in all these results are always easy. If you have 3 edge disjoint paths, you must remove 3 edges, is very easy. It's the other direction which is harder. Right? If you have a edge, if you remove 3 edges, to argue that there are 3 edge disjoint paths is the trickier part. Fine. Alright, so that basically, so the way this is proved, right, I will just give you a hint, I won't elaborate because I want to do other things, right. Apply vertex connectivity on the line graph of G. Right. I won't say anything more than this, but if you just read up Diestel or any other resource, the same, it's a simple transformation from the graph to its line graph. Vertex connectivity, edge connectivity gets mapped to vertex connectivity. Fine. Alright, so this finishes one thread that we were studying yesterday. Right. So there is also one another thing that I promised. I will show you how to generate a random directed acyclic graph. Remember, you want this to test your topological sort algorithms. Right. So one of the ways of generating this is so if there are n vertices in your graph, you select a random permutation of 1 to n. How does one select a random permutation of 1 to n? You use your random number generator in whatever programming language you want, right? Set the range from 1 to n, right, and sample, right, repeatedly numbers from 1 to n, right, and keep the n distinct samples. Drop a number if it is already repeated, right, or repeat and pick the number if it is sampled for the first time, right. You can do this with a die or something like that. If you have a 6-sided die, right, so you can do this, or you can basically sample n log n bits and treat that as a permutation. Another idea is to just simply take a coin and toss n log n bits. Why do I say n log n bits? Each log n bit will represent a number from 1 to n, right. So n log n bits will give you, right. So n integers, if anything repeats, you throw it out, repeat the experiment again. Fine. Now after selecting a random permutation, right, consider now consider each pair I less than j. This is just 2 for loops nested inside each other, right. For I equal to 1 to n, for j equal to I plus 1 to n, right. You toss a coin with probability half, again use your random number generator in your programming language, whatever you use, and decide whether to keep that edge or not to keep that edge. Fine. Consider pairs, right? Add to DAG with probability half, right? Otherwise, you just discard it. So clearly, you will get a directed acyclic graph, no doubt, because all the edges are moving forward, going from lesser index to greater index. So you will never have a cycle in the graph that you generate. So therefore, you have generated such a DAG. And now you can run your topological sorting algorithms on this, right? But remember, this is extremely important, right? This is a very important scientific process, that when you generate experimental data, right, your colleague or friend who is also doing a similar project should be able to compare his or her work, right, on your data. Therefore, it is important to, point number 1, have a separate program which will generate the data, put it into a directory, come up with a numbering of all the files, right, and publish your code so that somebody can generate the same data on a different machine, right, and then present all your experimental analysis on this generated data. The reason I am emphasizing this is that many times what people do is, when they do such experiments, they generate the data from the code at random at that time, run it and then plot something. Such a thing cannot be verified by anybody else at all, because if you discard the data that you was generated at random, the chance that you will generate the same data again, right, is low. So somebody else will not be able to validate whether your program was actually doing what you are claiming it is doing, right. So therefore, this approach ensures that another scientist can validate your work, right. So this is another thread that I had started that I have finished. So this is something that you should definitely write code and experiment for.